Rainwater harvesting can reduce potable water usage for your landscaping, toilet flushing, which also has a synergy with wastewater technology innovation credit. And as mentioned, it helps reduce your stormwater runoff, which has a synergy with Sustainable Sites Credit 6 stormwater management. You always have to do a cost-benefit analysis of your sustainable strategies and products. In this case, you have to look at how rainwater harvesting interacts with a sustainable design strategy such as a green roof. A conventional roof, only 20% of the rainfall evaporates, so it's a rainwater collection factor of 0.8. A green roof with 3 inches of soil has 33% less runoff, and so rainwater collection factor of 0.65. And for a green roof that has 5 inches of soil and maybe more vegetation, there's 54% less runoff, meaning that the rainwater collection factor is only 0.38. So it's half of what you would be able to collect from a conventional roof. So when you're doing your water budget calculations to see how much you need to collect to flush your toilets, use for irrigation or janitorial type of situations, you need to take into account what your roof is made out of. Rainwater harvesting can be on multiple scales. On a commercial scale, you typically use a cistern, as pictured on top. This is a school in Seattle on the right, using it as an educational kind of art feature in a main circulation area. And down below is more of a residential scale rain barrel that just has a screen input, flexible transparent hose, and then a barrel level meter showing you how much water you have left. In the bottom right corner, you can also see it used as an aesthetic feature in an area on a campus. This also shows you can collect water from flow through planters and things on the landscape as well. It doesn't have to just come from your roof. Next slide. Water efficient landscaping is an important topic to address because the typical suburban lawn alone consumes an estimated 10,000 gallons of water above and beyond the rainwater each year. This total exceeds the annual indoor water use for a household in total. That's why the first credit in the water efficiency category is water efficient landscaping, and it was more heavily weighted in LEED 2009 version 3. There are 2 to 4 points available for new construction, schools, and corn shell. So the intent of the credit is to decrease the amount of potable water, once again that's our drinking water, used for landscaping. There really is a water crisis being addressed with this credit, since landscaping accounts for 30% of the 26 billion gallons consumed daily. Up to 50% of the water applied by irrigation systems is lost in wind, evaporation, and improper maintenance and installation. I'm a golfer, not to pick on golfers, but this image really shows how much water can be lost due to those factors. The requirement for option 1 to earn 2 points is to reduce potable water consumption for irrigation by at least 50%. This is based on the midsummer baseline. There are various strategies to accomplish this goal through efficient irrigation systems, even moisture sensors, drip irrigation, captured rainwater and reuse, recycled wastewater, possibly through treatment on site, and carefully picking your plant species, density, and microclimate factor. You can also use imported gray water from a public agency. The LEED neighborhood development pilot project I worked on in Dubai was considering this, since on a municipal level they have a gray water treatment facility used primarily for irrigation. So in dry climates, this is very important to consider and advocate for on a district or city level. To achieve the full 4-point potential, you can use any combination of the methods in option 1 so that only captured or recycled water from on-site or important sources is used. So advanced gray water treatment is one example. This has a planter bed that is being irrigated from gray water reuse from dishwasher and shower, potentially dishwasher, but not most jurisdictions, going to a septic tank, sand filter, and a pump pit with some overflow available for even recharging the aquifer before it goes to the planter bed itself. Path 2 is to not use permanent irrigation system for landscaping. There is an exception for temporary systems that are removed within 1 year, and there's a possible addendum for even a year and a half. In order to not need any permanent irrigation, it really takes proper planning and understanding native species that are available for your climate. Xeriscaping is a type of landscaping that reduces or eliminates the need for irrigation. It's based on 7 principles: proper planning and design, soil analysis and improvement, appropriate plant selection, practical turf areas, efficient irrigation, the use of mulches to hold in moisture, and appropriate maintenance. Note that buildings have to have at least 5% of green space over their total site area in order to achieve this credit. So you can't just get the credit by saying you don't have any irrigation, and the reason being because you don't have any plantings. So using potable water for irrigation because of public health code concerns such as near swimming pools is also allowed. For schools only, applying this credit to school playgrounds and sports fields is optional. If it is included, you need to apply to the credits consistently. Strategies include a site map of existing buildings, sun and wind exposure, and that will help you determine 3 zones: high, moderate, and low watering. You don't want to overwater areas that only have low watering needs, and make sure that you concentrate water needed to the higher watering need areas. You need to diversify plants that will adapt to your bioregion and that are appropriate for these zones. You want to use minimum fertilizer and pest control. Growing up on a houseboat, this is near and dear to my heart, since those fertilizers then end up washing in to our water and streams. And drip, micro, and subsurface irrigation can reduce water demand by 30 to 50%. Here's a picture of a moisture sensor telling you how much water you have to supply per season or even daily based on weather data and moisture in the soil. And also a picture of drip irrigation. These can actually be better looking as well since you don't have big sprinkler heads exposed. Benefits include using native plant species. You have less maintenance since they're meant to be more durable in that specific bioregion. They require less fertilizers and pesticides, which is also a cost saver and lower maintenance. Helps with our waterways staying clean and aquatic nature within those. And also it can shade hardscape, which can help with heat island effect, which is also a synergy with Sustainable Sites Credit 7. As you see here, that gets into related credits and synergies with site development, heat island, stormwater. It can also integrate bioswales and flow through planters that help with stormwater design. And then optimizing energy performance as well, since some of these irrigation systems require more energy than others. It really needs to be regional specific. Hot, dry climates seeing drought-tolerant plants, rocks, can even be used as landscaping. Xeriscaping replacing turf can be a huge cost saver. In hot, humid climates, native plants with moisture sensors have a better return on investment. And in cold climates, you want to pay attention to hardy native plants that can survive the harsher winters. For operations and maintenance, you want to consider submetering, making sure that those are recalibrated and maintained. Site landscape maintenance plan. Gray water system manual with manufacturer contact info, and always educate facility managers that are new and continuing education for facility staff that have been on for longer. You need to provide guidance to contractors about when and how to temporarily irrigate to establish plantings to make sure that's done a proper way and that the temporary irrigation can be removed within 1 year. For landscaping, there is a calculation that needs to be done to determine the landscape coefficient, which is the volume of water loss via evapotranspiration, and it's species dependent. 3 factors you need to take into consideration are species factor, which is the variation of water needs. If there's no irrigation required, then that KS species factor equals 0, which means the landscape coefficient therefore equals 0 because it's a product of these 3 factors. The density factor is the total leaf area of a landscape area. For example, 0.5 equals 25% ground shading from trees, which is low, and 1 to 1.3 equals trees and understory shrubs, which is higher. So really the larger the planting, the higher that density factor. Microclimate factor, KMC, takes into account the environmental conditions specific to landscape, including temperature, wind, and humidity. This can be affected by where the plants are placed in relationship to even buildings on site. 1 equals evapotranspiration that is not affected by surrounding buildings. 1 plus equals increased effect from heat absorbing surfaces and wind tunnel effects. So large parking lots, high buildings, and other partitions and landscape features can have an effect. First thing you need to do is calculate your reference evapotranspiration rate for the region. It's project specific and it's constant in both your baseline case and your design case. To determine your evapotranspiration for a project, you multiply your evapotranspiration for your project site times your landscape coefficient. Remember that site-specific evapotranspiration rate is constant for the baseline and the design case, the ETO, but the evapotranspiration for the project is specific to the landscape coefficient per the species chosen in that landscape plan. Water efficiency credit 1, water efficient landscaping. 2 to 4 points available. Here are the calculations. Step 1, establish your design case. You need to sort the landscape into major vegetation types and determine those 3 factors for each zone. So that's your species, microclimate factor, and density. Then you need to calculate the landscape coefficient, which is equation 1, which we will look at. Regional evapotranspiration rate, which can be found in regional agricultural data, and some irrigation controllers have that information included, such as the rainbird. You also need your project-specific evapotranspiration rate, which is equation 2 that we'll get to. And you also need to determine your irrigation efficiency. Now, if applicable, you have to include your controller efficiency, which could be moisture controls or weather-based controls. And if you're reusing any water, you need to include that volume. That could be rainwater harvesting, recycled gray water from your sinks and showers, or treated wastewater for things such as a living machine or anaerobic digester. On site, this is a really great reuse. Step 2, you need to establish your baseline case. So that's setting everything to average values. So your species factor, your density factor, and your irrigation efficiency are all set to conventional baseline standards. Things that remain the same for the design and baseline case are your microclimate factor and your reference evapotranspiration rate. From the baseline design case, you can then calculate the percent reduction. On Lead Online, this automatically tabulates for you. Here's an example chart of landscape factors, including various vegetation types. You can see the difference between the species factor for trees and shrubs. For trees, this is slightly higher. Density factor, trees are also slightly higher than shrubs, for example. And the microclimate factor, comparing these various vegetation types. So to calculate the landscape coefficient, you multiply these three area characteristics. Examples of irrigation types and their efficiencies are in Table 2 below. Sprinklers have a lower efficiency than drip irrigation, so you actually increase your efficiency by 30 to 50% with just drip irrigation. To continue our calculations, use equations 3 and 4 displayed below to calculate the total water applied and total potable water applied for each landscape area in the installed case. So as you see in equation 3, the design case is the area of vegetation times the evapotranspiration rate over the irrigation efficiency. And then if applicable, multiply that times the controller efficiency. Equation 4, you then take that total water applied, calculated in equation 3, and subtract the reused water if applicable. That's, once again, we're using rainwater harvesting potentially or gray water use on site. For equation 5, you're calculating the total water applied in the baseline case, which equals the area in square feet times the evapotranspiration over the irrigation efficiency times the 0.6233 gallons per square foot per inch. Next, in equation 6, you're calculating the percentage reduction of potable water. So it's your percentage reduction of potable water. So you have the 1 minus your design total potable water applied, or the baseline total water applied, times 100, and that gives you that percentage. Equation 7, you need to calculate the percent reduction in total water. So that's 1 minus the design total water applied over the baseline total water applied times 100 to get that percentage.